My work title is Type 4 Creep Cracking of Welded Joints, Numerical Study of the Grain Size Effect in the Heat Affected Zone. Let me introduce the problem. We know that type 4 cracking is a creep cracking which occurs at the interface between parent metals and heat affected zone material in ferritic steel weldments. It occurs in a special region of the heat affected zone we call fine grain heat affected zone. Just a look to the experimental evidence. We know that typically at higher stress levels, type 4 fracture no more occurs, like in the first case here shown. Then another important evidence is that suppressing grain refinement or increasing grain boundaries hardening, the type 4 fracture is inhibited. So another important evidence is that the cracking, this kind of fracture, occurs from localized formation of nucleation and growth on voids. The consequence of the onset of this type of fracture, of course, is the reduction of the expected creep life. And we observe a greater reduction of creep life at lower stress, as shown here on data taken from literature. So the aim of this work is to investigate the type 4 fracture mechanism in a 9-chromium steel, P91 steel. And I will try to simulate the onset of type 4 fracture with a damage mechanics approach. And performing a parametric study, we try to clarify the rule of the diffusion control of the deformation mechanism for this issue. Here I summarize the approach. Basically, we have a constitutive framework for creep deformation accumulation and creep damage. We have calibrated the entire model for the P91 steel, and the most important thing that in that case we have a calibration made just on the base metal, and to predict the onset of type 4 fracture, we just assuming a grain size distribution along the weldments. So the cross welds are simulated according only for the accounting only for the different grain sites in the heat affected zone. Performing parametric analysis in detail, I will show you some simulation. I will conclude with some important results. I will go quickly on some part of this modeling, because the next presentation will be focused on a validation of the same model for the minimum creep rate prediction for another steel, but the details will be given in the next presentation. Basically, we want to perform an accurate description of the creep strain accumulation in each regime: the primary creep stage, secondary creep stage, and tertiary creep stage. In particular, for tertiary creep stage, for that kind of materials, so we have to distinguish two phenomena. Microstructural, we see here, this is in the graph, a first creep rate increase due to microstructural barriers depletion that we can call damage, but it's a microstructural damage probably. And to describe the entire tertiary creep stage, we have to add we have another contribution due to the second part. The second increase of the creep rate probably is due to void location and not. And only the second mechanism rules the failure. Here are summarized the equations I used. We have the actual creep rate obtained starting from the minimum creep rate, multiplied an hardening function and a recovery function. It's important that the minimum creep rate is given as a sum of two contributions. The first one is dislocational contribution, and the second one is diffusional contribution. The H function is an hardening function to account for primary and transient creep. The recovery function, we need the recovery function to describe the initial creep rate in a pseudo tertiary stage, the initial stage increase of the creep rate in the tertiary stage. Okay, in particular we have to describe just quickly the separate contribute to the minimum creep rate. The dislocational terms is a general power form to account for non-linearities in a double log plot when we are in a purely dislocational creep regime. And the most important thing I want to stress now is that the diffusional contribution has an explicit dependence from the main grain size in the microstructure. So the larger the grain size D, the larger the creep rate at low stress is obtained. For what concerns the failure, we use a cavitation model. It's a cavitation, it's a damage model derived from the continuum damage mechanics. It's a formulation time independent. We call the purely mechanical damage is controlled by strain accumulation. Damage initiates when threshold strain is exceeded. Failure occurs when the critical damage is reached. And the model we use is sensitive to the stress triaxiality. Here are reported some equation, but the main features of the model is that damage has the effect to increase the stress, so we use an effective stress. Was derived in '97 by Bonora in the framework of the continuum damage mechanics proposed by Lemaitre. It's a tropic damage. Here you can see the kinetic damage law. That is a linear damage equation. We use damage that accumulates only under tensile state of stress. And finally, take into account the effect of the stress triaxiality by the function Rho. For the scope of this work, the model was calibrated on the available data and literature relative to the P91 steel, and we have a good transferability in stress, temperature, and for primary creep stage, for primary, secondary, tertiary creep stage. And in order to simulate the crosswells behavior, the most important thing is to introduce as an input in the model a state variable to assume a grain size distribution along the gauge length of the samples. So you see here the mesh I used to simulate the crosswell sample. And this is the idealized green sites assumed in the heat affected zone, starting from about 40 micrometers, and far away the heat affected zone is more or less the same values, but in the heat affected zone we have a sharp degrees of the grain sites. Okay, we can see the effect now of our modeling in terms of grain sites, and in particular I performed two simulations. I will show you in details the results of two stress level simulation. The first one at 50 MPa at 600 degrees C, when the diffusional mechanism is the dominating mechanism. And the second one had a higher stress, about 150 MPa at the same temperature, when this dislocation mechanism is the dominating mechanism. As you see in our modeling, introducing the effect of the grain sites at low stress, there is a change in prediction of the minimum creep rate due to the effect of the grain sites, while at higher stress this is negligible. Okay, here we can see the results. In the first contour plot is shown the creep strain accumulated at failure. You see a very localized creep strain, and like the creep strain is also localized damage at failure. You see here some the initial crack due to the localization of damage. And if we compare the same results for higher stress, you see a completely different strain accumulation, less localized, and the same thing in this graph is reported in terms of equivalent creep strain versus the gauge line. So we predict exactly the total elongation and the location of the for fraction. Under our point of view, this is due. This is, of course, under my point of view, good results, and is partially due to the effect of the triaxiality. Because when diffusional creep is dominating, a very high stress triaxiality develops as a result of inhomogeneous deformation. Means that the material surrounding the heat affected zone has an effect of constraint, and if we can see this graph clarifies this behavior, because in the fine grain heat affected zone you see a very high stress triaxiality, almost 4, like the stress triaxiality at the crack tip of without a crack. But otherwise, in the second case, the stress triaxiality is very low. Is higher than just at the beginning of the failure, but very low compared to the stress triaxiality in the heat affected zone. Of course, the damage formulation is sensitive to the effect of triaxiality, so we have a localization damage too. In terms of creep life and total elongation reduction, this is our results. We can, in the first graph, this is a classical Mankoman-Grant visualization, you can see compared the base metal with the cross-welds life. We predict pretty well the reduction of life and also the total elongation of the cross-welds reported in the second graph. In conclusion, according for accounting for both diffusion and dislocational creep, it's possible to predict the condition under which time for fracture can develop. The proposed approach requires the knowledge of grain size variation along the weld, and this can be eventually evaluated by a given VPS. And the development of high stress axiality play as an important role for this issue under our point of view. So the presented creep plus damage modeling approach seems to capture most of the features observed in the cross-weld experiment, and we are studying again on this way. Thank you.